Hi there, CTM students. Welcome to the lesson for 13.8. Let's get right into it. We're going to be talking about correlation, linear correlation specifically, and regression, and what all that means and what all these terms here mean as we go through this lesson. Alright, first off, I want you to write down this formula. This is going to be the linear correlation coefficient formula. You may have heard something called a line of best fit. We're going to get to that a little later in this lesson. Before, maybe in your other math classes, you've just kind of drawn it in and saying, and may have said that, oh, this looks like it's probably about where the line of best fit is. But there's a way to do that, and to do it extremely accurately, to do it precisely, and we're going to learn that way today in the lesson. But one of the other things we need to learn about is this linear correlation coefficient. And so this R stands for just that. So R is the linear correlation coefficient, and in a different color, put this off to the side for me, please. This is always between, I'll put B/W for that, between -1 and +1, -1 and 1 inclusive. So that means it can include those numbers. If it's a perfect correlation, if everything is exactly on the line of best fit, it would be -1 or +1, depending on what way it is sloped. If it's a negative slope, it's a negative correlation. If it's a positive slope, a positive correlation. And then this is going to look kind of messy at first. I'll be honest with you. This is going to look like a lot, but it's really just a bunch of arithmetic, and if anything, it's just tedious. It's not difficult at all, I don't think. It's just tedious, and you got to be careful with what you're doing with your numbers. So it's the number of data values, and then this just means the sum of whatever is next to it. So it's the sum of the product of x and y, whatever those things are. Well, why don't I just write this all down? I guess I'll explain as I go a little bit here too, though. So the sum of the x values times the sum of the y values, all that is over the square root of n, number of values, times the sum of the x squared values minus the sum of the x values squared. So this is all under the square root here. And then we have this times one more square root. It looks exactly like this, just with the y's. So n, sum of the y squared pieces minus the sum of the y pieces squared. And so why this formula works, we're not getting into that in this class. That's beyond the scope of this class. But this is the formula we're going to use to find the linear correlation coefficient. And from there, I want to talk about a couple of tables, or actually one figure and one table. So a figure like this, don't need you to write this down, but I do want to point some things out here. You'll notice if I were to draw a line of best fit on this one, it fits perfectly onto that. So this is just a sketch here. A line of best fit on this one, same thing. Fits perfectly. All the data points are right on that line. You have here R equals -1. That is the strongest negative correlation. So everything's perfectly negative. Here everything's perfectly positive. Now here they're still pretty close to being on this line, but they're not all right on the line. But you're going to have R is bigger than 0, and you're going to have this strong positive correlation. Notice here as I continue to go through here, the data points are getting farther and farther away. Some are close still, but some are farther away. You're still going to have a positive correlation with something like this, but it's going to be moderate to weak instead. And here there's really no line that best predicts where that is. That's why they're saying no correlation. Same thing here. There's really no good line to draw that predicts where the data is going to be. But here, yeah, it's generally trending negative. Here it's a lot stronger negative. It should be down there a little bit more, I would say. But that's generally what's going on. So these are all negative correlations. Here, here, and here, these are all positive, and then these two, no correlation. And then this table we're going to use a little later. So right now just know that we're going to come back to this. So table 13.8 is going to be talking about whether the things are actually correlated or not. So one more big equation here for this lesson, excuse me. One more big equation for this lesson. This is the equation for the line of best fit. So there's a way to precisely figure this out. It's not just a random line that looks like it might fit the data, but this is going to be another phrase for that is the regression line, regression line. Or you might also hear the least squares line. I kind of like that one best personally because it describes it more. This is where if you draw a line like this, let's go back a couple, if you draw a line like this is where the data points are in total the shortest distance away from the line. So it's the line that best fits the data, in other words. The least squares line is another way to say that. Okay, what is that equation? It's, well, this shouldn't look familiar from algebra, y equals mx plus b. So that's slope-intercept form. But what do m and b stand for, or what are they? Here's what they are. So this is where m equals, and these things should look familiar from the other equation we had. So it's the sum of the xy products, and that multiplied by the number of things you have. It's the sum of the x and the sum of the y's all over n times the sum of the x squared pieces minus the sum of the x pieces squared. And b is going to be a little more easy to write out here. It's the sum of the y values minus m times the sum of the x values all over n. So yeah, this looks like, be honest with you, it looks like a lot. It looks like, oh my gosh, how can I possibly figure all this stuff out? This seems ridiculous, Mr. Wagner. Why are we doing this lesson? Blah, 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 blah. Oh, calm down. Just calm down. You're going to be fine. Everything's going to be just fine. So this right here, notice that's the same thing I'm using right here. Same thing on the top there. And then this part is the part that's under the square root over here. So actually, once I find what this is and what this is, I can go right to this equation and plug those numbers in directly rather than individually plugging things in. So that'll save us some time. We're going to do just one example here, but we're going to do 4 different parts, and we're going to use all these ideas that we've talked about with this example. So one example, but 4 parts to it. Make sure you're focusing as always and paying attention closely, trying to not only just write things down. That's not the point of doing this, okay? The point of doing this is, yes, you're providing notes for yourself later on to look at, but you're also thinking about it. You're also learning right now. You are trying to comprehend, you're focusing, you're paying attention, and you are soaking it all in. So 7 students provided the following data about the lengths of the time they studied for an exam and the grades they received on the exam. And here's the data. So let's make a little table. This is what happened. So we're going to have 7 students. I'll call it just, instead of names, we'll just go with student 1, 2, 3, 4, 5, 6, and 7. And this row will be the time in minutes that they spent studying. This row will be their grade as a percent. Since we can't really plot letter grades very easily, we can plot numbers though. Percents are just the numbers representing the grades. And so let's say student 1 was 60 minutes and they got a 77% on the test. Student 2, they said 35 minutes. We're rounding these to the nearest 5 minutes here with the times. The grade was a 63%. Student 3, 90 minutes, so an hour and a half, and 82%. Nice job, student number 3. Student 4, 120 minutes, that's 2 hours, but it paid off, 96%. And excellent work, student number 4. Do you have a name, student number 4? No, you're just student number 4? Okay. I'm sorry. 30, 80, 75, 85, and 10. Uh-oh, 10. Oh, yep, that's what happens sometimes if you don't study much. If you're not ready for that thing, be careful. Okay, so right here and right here, I'm going to define a couple terms quickly. This is, or talk about what the terms are in the context of this example. Probably a better way to put that. This is an independent variable right here. So these times, they do vary, therefore they're variables, but they're independent because they're not depending on anything. The number or the amount of time the student spent studying didn't depend on something else. The grade, however, we're saying there is this correlation, there's this relationship between these two things. The grade is based on the time put into studying. That's what we think, at least. So we're trying to check that. Therefore, this one is the dependent variable. It's depending on the other variable. So yes, it varies. That's why it's a variable. It varies from one thing to the next. And it depends on the time studied. That is our assumption right here. And we're seeing how strong of a connection there is. So write those things down in a different color for each part there, pointing to things there. And then let's get started with the parts of this example. So part 1, I want you to draw what is called a scatter diagram. Scatter plot is another way to say that, but our book refers to it as a scatter diagram of the data. And for me, I'm going to put a grid in the background on this to make the graph really nice. I would suggest getting a ruler if you have one, or at least finding something straight like the edge of your ID, something like that, to make a nice graph here. The nicer this graph is, the easier the rest of this one will be. Alright, so that should help significantly here with this grid in the background. I'm going to make each one of these worth 10 as I hop up, and I'm going to start at 50 and go to 100. As I go this way, this is going to be, my x is always going to be my independent variable, my y is going to be my dependent variable. And so let's draw some axes here. We are with that. And then as I go up here, I'm going to start at 0, but I don't want to include 10, 20, 30, 40, and 50. I feel like that's not really necessary. And so I'm going to put a little break right here. I'll draw that in just a second. That should be good right there. But something like that is representing the break in the line. So let's call this 0. And this is going to be, again, my independent variables here, my x values. And then y is going to depend on x. So these are going to be my y values. This is going to be my, I don't think I can write sideways, so just a second here. Okay, so I've written dependent this way. This is going to be the independent variables, and the y values depend on the x values. And as I go up here along this axis, I'm going to make each one worth 20. This is going to be 20. This will be 40, 60, 80, 100, and 120. Looks like I could have made this a little bit smaller. Why don't I do that here a second? Okay, so I just moved that in this way a little bit, and then here I'm going to say right there is going to be 50%. This is 60%, 70%, 80%, 90%, and up to 100%. And notice my scale stays the same, so keep these evenly spaced, otherwise your graph's going to get thrown off. And then this represents, this is the grade received. Down here is going to be the minutes studied. So let's write those things in. Minutes studied, and then I'm going to write it here and then rotate it and put it over here, grades received. And so make sure you write that there, grades received, minutes studied here. Again, this y, or these y values, are dependent upon the minutes studied values. And so let's plot these points. We've got 60 and we've got 77. So go to the right 60, go up 77. Halfway 75, you're going to go a little bit higher than that, but definitely lower than 80. So that's about where that one should be. 35, 63. So 35, this is going to be 30, so halfway in between 30 and 40, and then 63 right about there. Be careful with your drawings here. Draw it as best you can. There we go, I think that's a little better. 90 and 82, so halfway in between 80 and 100, and 82 right about there. So that one's good. 120 and 96. So 120 up to 95 is right there. So just a skosh above halfway. We'll be right about there. 30 and 80. 30 right there. 80 right on the line right there for me. You can use your blue lines on the paper if you're using normal paper. If you're using graph paper, that might be a good thing too. You don't have to use graph paper though to do stuff like this. And then 75, 85. So here's 70, go a little bit farther than that. 75 and 85, halfway in between, right about there. And finally 10, 54. So 10, right about there. 54 is going to be just under halfway there. So before, in the past, you've drawn lines of best fit. Yeah, it would be about here-ish, but we're not going to draw that in until later. So we're going to save that for later once we actually know the true best equation, line of best fit. Once we got that, then we'll come back to this part and fill that in. So we've just drawn the scatter diagram of the data for right now. Moving on now to a second part, to part B. So part B, let's now find that linear correlation coefficient. That's what we're going to do next. So determine the correlation coefficient. Excuse me. So for this, let's draw a horizontal line this way, and then I'm going to draw in yellow. I'm going to make a few more. You can just use the blue lines for this, but I'm just going to keep my data straight this way. So these are like the blue lines on your paper, most likely if you're using the wide ruled or college ruled lined paper. We've got those things going on there. I need to make 7 rows. So 1, 2, 3, 4, 5, 6, and then the 7th one I can use the black line now. This is going to be where that ends, so make a darker line there, and then this will be your sums or your total values down here. And as we go across this way, I'm going to put in some other lines going down this way. So I'm going to make 5 columns about the same width. Those first 2 can be a little bit smaller, and then these other 3 should be just a skosh bigger. I'm going to use skosh again. I like that word. It's a good word, isn't it? Oh yeah, great word, Mr. Wagner. Skosh. I like it. Thanks. Good to hear. And these values, you're going to have x, y, x squared, y squared, and then this one will be the product of x and y, x, y, just like that. Down here, these are your sums, or you can use that symbol for sums instead. So these are the sums of all these data values right here, and so on. And so what were your values for x and y? These are going to be the x values, and these are going to be your y values. So let's write that in a different color right here. These are going to be my x values, and these ones are going to be my y values. Remember, again, these are dependent. Y values are dependent. The x values are the independent ones. And so let's fill that in. And first we'll have, let's just put all the x values first. So 60, 35, 90. 60, 35, 90. We've got 120 and 30. 120 and 30, and then 75 and 10. Those are my x values. That look a little better. 75, okay, and 10. And then the y values 77, 63, and 82. 77, 63, and 82. 96, 80, 96, 80, 85, and 54. Okay, so now we need to find what x squared is in each case, find what y squared is in each case, and find what x times y is in each case. That will require the use of a calculator. Okay, so right now we're learning what I would call the long way of doing this. You have, or there are, you might not have one yourself, but there are statistical calculators out there. Graphing calculators generally have the capability of doing these things very quickly. They have a program that's all set up where it figures all this stuff out. It's all programmed into the calculator, and it does it quickly. But we're going to need to know how to do this the long way. We want to learn that so we know what our calculator is actually doing, and hopefully appreciate what it's doing a little bit more. I really didn't need to do 60 times 60. I know 6 times 6 is 36, and I can just add 2 zeros to that. So I'm going to fill in the easy ones. 9 times 9 is 81, so add 2 zeros to that. 12 times 12 is 144, so I'm going to add 2 zeros to that since it's 120 times 120. 3 times 3, that's 9. Add 2 zeros to that. 10 times 10 is 100. So just 35 and 75, those are ones I don't know off the top of my head. I have done this work already, but I just want to double check it. I feel like it's going to be, if I mess something up here, it's going to mess the rest of the whole problem up. So I want to make sure this stuff is all good. So I'm going to double check, verify what I had from before in every single case here. And so let's see, 75 times 75, or 75 squared, in other words, 5625, yep, that's what I had before. The only easy one to do here in my head that I'm thinking of right now at least is 80, so 8 times 8 is 64, and you got that many hundreds. 77 times 77, that's going to be 5929. 63 times 63, 3969. And so you don't have to do this on a calculator yourself, but you're seeing what it takes to do this. As I go through this, 82 times 82, you're going to have to do this with each individual data value. I need to see this kind of work. 96 times 96 is 9216. So you'll notice this is not difficult to do. It's just kind of tedious. But 7225 for 85 squared, and then 54 squared is going to be 2916. And now this column, x times y. So I'm just taking this value times this value. So 60 times 77. And just keep going down the list like that. 4620. Next I'll have 35 times 63. 2205. 90 times 82. 7380. 120 times 96 is 11,520. 30 times 80, that one I can do in my head, that's 2,400. 75 times 85, that's 6,375. Finally 10 times 54, that's an easy one to do too, that's 540. I just can't draw my fives very well though. Let's try that one more time. There we go. So 540. So now what I need to do, I'm just going to double check all these with the work I had done before. Just want to verify that quick, and then we will take the sum of each column. Okay, so that all looks good to me. Now I'm just going to take 60 plus 35 plus 90 plus 120 plus 30 plus 75 plus 10. If you have a calculator that lets you see everything you typed in, that's really nice, because then you can double check before you press enter to see if you made any mistakes. Should be good to go for me there. 420 it is for the sum of the x values. 420 minutes total that were studied by the 7 students together. Now we're going to add 77 plus 63 plus 82 and keep going with all those y values. And some double checking that looks good to me. Got it all there. 537 is what that is. Now I'm going to sum up the x squared values. 3600 plus 1225 and so on. And let's see if I got that. Good, that looks good. Yep, so I'll enter 33,950 so far, all matching up with what I had before as well. So feeling pretty good about things. Feeling pretty good about life right now. Yeah, it's going well right now. I'm doing math. Things are coming out correctly. Doesn't get much better than that, does it? No, of course not. I love math, Mr. Wagner. Of course you do, because it's amazing. Let's see. Alright, 42,379. It is 42,379. And finally, let's sum up those XY values, the product of X and Y. 4620, 2205, 7380, 11,520, 2,400, and 6,375, and finally 540. So how do I look there? Looks good, looks good. Yep. So that should work out there. Yep. You know what that's from? Props to you if you do. I hope you do. Okay, so we've got all these values here, and from this point we're going to start plugging some things in. So now I can put R equals, I have all the values I need to plug into the equation for that. So R equals, I'm going to write down the general formula again. This is just coming from back too far there. Back at this one. So we're going to take this formula, plug everything in there again. We'll write it out in general one more time just to get that practice. Is this a formula you're going to have to memorize? No, I'm not going to make you memorize this. Don't worry about that. I feel like I should move this a little bit this way, though, to put it in the center of the fraction a little bit better. So let's see. This minus the sum of the x's times the sum of the y's. All that is over the square root of n times the sum of the x squared values minus the sum of the x values squared. And then that times the same thing with the y values. N times the sum of the y squared values minus the sum of the y values squared. So let's plug things in here. What does n represent? We haven't talked about that yet, but let's write that off to the side here. N is just the number of data values. Like it's been in the past, it's still that same thing. So the number of data values, I had 7 data values. So this is going to be a 7 in the equation. So 7 times the sum of the xy values is right here. This was that column. Here's the sum of the xy values, 35,040. Next up, we've got the sum of the x values. So here's the x values. The sum of that was 420. So this will be on the top here, 420 times the sum of the y values. That would be some of the y values here, 537. So that goes right here. That's the top of our fraction. And now for the bottom of the fraction, we got the square roots of n again. That's the number of values, so that is 7 times the sum of the x squared values. Here's your x squared column, 33,950. We have that minus the sum of the x values, so there's 420 showing up again. We have 420 and we're squaring that. So this is the square root of all that times the square root of n again, that's 7. Sum of the y squared values is 42,379. So here's 42,379 minus the sum of the y values squared. The y values, that was 537, so we're going to be squaring 537. So again, I reiterate this. Notice the math is not difficult. It's just basic arithmetic and a little bit of square roots here. It's a basic fraction. It's just tedious. Yeah, just being straight with it. It's tedious. It's tedious for me. It's probably tedious for you. But we just need to work out the numbers here. That's why we're only doing one example here, and that's why I'm not going to make you do a ton of classwork like this, or you're going to have to do like 10 of these or anything crazy like that. So don't expect to have to do too many of these. But this is the beauty of calculators, the beauty of graphing calculators and computers. They can do these calculations for us in fractions of a second rather than taking all the time that we're doing to do this. So just working out the numbers here, that was this times this, 245,280. We'll have this minus, we got 420 times 537 is 225. 540. Then we're going to have this over. Okay, what's 7 times 33,950? That is 237,650. 237,650 minus what's 420 squared? That is 176,400. So we're going to have this square root of those two things subtracted times, this will be 7 times 42,379. That is that number, 296,653. 296,653 minus 537 squared. 288,369. 288,369. Okay, so the square root of all that want to just double check and verify this with the work I had done before a second. Okay, it looks good, so we will continue. We're going to subtract this here. 245, 280 minus 225, 540. That gives me 19,740 on the top of the fraction. And then down here I can simplify under the square root parts, both parts here, so this would be 237,650 minus 176,400, that is 61,250. We have that times whatever this is, so that's 296,653 minus 288, 369, 8,284. Okay, and now at this point I feel like we've simplified enough things where we can just type in the rest into a calculator. The problem with doing that up here, you could do that, but you just have to be really careful with the way you put parentheses, because your calculator knows order of operations. It's going to, if you just type this all in as a string, it would be taking this, and it would be taking this, and then before it would subtract, it would take this product and divide it by this, and so we would want to have parentheses around this whole top part. We'd want to have extra parentheses here. Don't write this what I'm about to put in yellow, but we'd want to think of it like that, as there's being invisible parentheses here, and kind of being invisible parentheses here. So yes, you could get away with that with doing this all in one shot in a calculator, but just be really, really careful if you're going to do that, because remember, your calculator knows order of operations. So at this point, I'm going to show you the best way to type this in my opinion, would be like this. So 19,740 divided by, think of this again being in invisible parentheses right here. You don't have to write that in, but it's like that's together here. So we want to take this and divide it by, these two things need to get multiplied together first before I would take that and divide it by these things. If you didn't put this in parentheses here and here, it's going to take this number and divide it by the square root of this first, and then multiply that whole thing times that, which would give you a different answer. And so we're going to divide this by, I'm going to use my parentheses here, divide this by, include this in parentheses, the square roots of 61,250. I'm not sure if I can do that with this calculator. I might have to do this a different way with this calculator. Let's see if that shows up. Nope, I'm going to have to do this a different way. I think we're just going to have to trust the work I did before then on this one. So the square root here, and then this, that gave you, so this calculator that's coming up on the computer not giving me the option, it looks like, or I just don't know how. If it does have that option, I'm not sure how that works. But if you're going to put this into a calculator, at this point put parentheses here and here, and so divide that, or at least multiply these two things together first, and then take that number and divide that by whatever you get for that. You should get 0.876. I did that pretty carefully before, so I'm pretty confident about that answer. This is your correlation coefficient. So all that work, yes, that was 2 pages here, 2 slides just to get one little number. This R value is approximately 0.876, but a very important value. That's a pretty strong positive correlation. Why is it a positive correlation? It's because the slope is positive. It's going up as you move left to right. And so let's now check out part C. This part should take a little less time than we just did there. But part C, determine at a level of both 5% and 1% significance if a correlation exists between the time studied and grade received. And so I'll put SOLN for a solution on this one. We have to go back to table 13.8. So I had put that in a slide previous to this. We're going to go back to that table, refer to that table for this problem. We're going to find the alpha values. The alpha letter looks kind of like that, like a little fish sort of. So find the alpha values for n. We have 7 different numbers, different sets of bivariate data. It's called bivariate data because it has 2 variables, like bicycle has 2 wheels, bivariate has 2 variables. So let's go back to the table here. Here it is. So this table, you don't have to write this down, you don't have to memorize this table. Like it says down here, where this is coming from or where these values are from, it's beyond the scope of this text, beyond the scope of what we're learning in this class. But this is called the critical values. It's also called the Pearson correlation coefficient. So these are these Pearson correlation coefficients here. For n equals 7, if it's going to be 5%, what this means is that there's a 5% chance that the values would not be correlated. I'm not saying that very well, I don't feel like. Let me think that through a little more clearly, and then I'll state it again. So I think that the better, more clear way to say this is with 7 data values, as long as your correlation coefficient, your R value, is this high, there is a less than 5% chance of the data not being correlated. And as long as your data value or your R value is this high, there's actually a 1% chance or less that it's not correlated based on that. So we're using this table. So this is just saying what's the if a correlation exists. Yes. So is there a correlation based on a 5% level of significance and a 1% level? Our value was 0.876. It's pretty darn close right there. This is 0.875. So yes, 0.876 is higher than this one, and it's also higher than this one. So you can say not only is there a 5% significance level, there's actually a 1% significance level. So even better, we can use that and be very, very sure, 99% sure, that there is a correlation between this data. Meaning there's a correlation between the amount of time you spend studying for a test and the grade you get on the test, if this were a true set of data. And I think that generally is true as well. If you spend more time studying, you generally do better on the test. But that might vary. You might have those people that can just soak it in the first time around, hardly have to study a lick, and then get a great grade. And you probably don't like those people very much because that might not be you. Maybe that is you though. So for alpha, that 5% significance level, was that true? Yes, that was true, because R equals 0.876. That's what we found from our last part. That was our R value right there. And 0.876. Our book says strictly greater than, but then it doesn't say what happens if it's equal to. So I'm assuming that it should be greater than or equal to 0.754. This is the value that was in the table back here, 0.754. That was that one right here. And then the other one, we're comparing 0.876 to 0.875. It is greater than or equal to, and so we can say the same thing for an alpha value of 0.1. We would also say yes. Again, you have R as 0.876, and 0.876 is greater than or equal to 0.875. If this were 0.832, something like that, it would not be greater than that, so you could not say that with this 1% alpha value. You couldn't be that sure of it. And one more quick note to make with this one. I want to make this note: if sometimes you're going to have these negative correlation values. So if you get to a problem like this, it asks you to find this sort of thing with negative correlations. If R is negative, it's real simple. You just have to take the absolute value. So if R is negative for a problem like in part C here, use the absolute value of R. That's what those symbols mean again. So the absolute value of R for comparing to the values in table 13.8. Okay, so make sure you do that if you get to something like that. And let's make one more note before we move on to the last part. These values, again, where did these come from? These were coming from the values in table 13.8. So the values were from table 13.8. Okay, and then finally, let's check out part D. We haven't done the equation yet, so that's what we're doing to finish up here. So find the equation for the line of best fits, also called the regression line, also called the least squares line. So line of best fits, and graph the equation on a scatter diagram. Okay, so how do we find that equation? Let's put solution in here. We have to find y equals mx plus b. We got to know what m is, and we got to know what b is. So m was this value, it's the number of terms, times the product, sum of the product of the x and y values, minus the sum of the x values times the sum of the y values. And you have that over n times the sum of the x squared values minus the sum of the x values squared. So it all looks kind of crazy at first, but we've done this work already. Let's go back and see where we see this stuff already. So there it is. There's the top part. It's exactly the same as the top part for the m value. And so I've already done this work. We simplified this. All on the top eventually got down to 19,740. I see no reason why we should do that again. So let's just put that right here. 19,000, not 470, 740, sorry. 19,740. And then on the bottom, we've actually done this work already too. So where is that value? This is, went too far there. Here it is. This n times sum of x squared minus sum of x squared would be whatever you have under here, simplified, and the n is 61,250. 61,250. And so from there, you put that into a calculator. Let's do that right now and see what we got. So 19,000. I think I need to clear this just a second. 19,740 divided by 61,250 gives you about this. So about 0.32 if you round that off to the nearest hundredth, approximately 0.32. And so when you look at these notes later, I want you to remember where these came from, these values. Let's circle that in a different color, circle that in a different color. Make the same note about both of these values, that these values are from part B. And let's go back to part B as well and make a little note of that we use these right here and right here. These are used in part D. So making references back and forth between these rather than doing all these tedious calculations a second time. Let's just use what we've done already. Okay, and so we've got that as my correlation value, so let's circle that, or that as my slope value, I should say, not correlation value. Correlation value already figured out. I do need to figure out my y-intercept, my b. And so this was the sum of the y's minus m. M is what I just figured out here. It's the slope times the sum of the x's. All that over n, the number of terms. And so I'm going to put approximately equals 2 here because I used a rounded off decimal for m right there. And the sum of the y values, that from the table back here, was 537. The sum of the x values, remember, was 420 as well, so I'm going to plug those things in to the equation here. So we have 537 minus 0.32. Where did that come from? That comes from right there. So 0.32, let's make a little arrow with our normal color there. And the sum of the x values, 420, over, this is over 7. If you work this all out, let's just double check my work from before on that. 537 minus 0.32, and my calculator here knows order of operations, so it's going to take this times 420 first and then subtract that from 537. So that gives me 402.6. That over 7 is approximately 57.51. So here's my B, here's my M right there. So I can say therefore the line of best fits equation is, you're going to take your y equals mx plus b, replace m and b with what we calculated them to be, and so this would be 0.32 x plus 57.51. And now we still need to graph this, but I'm not going to draw a whole new graph. I'm just going to go back to part A. You can do the same thing. So the graph of this equation is included in part A. So let's go back to part A to finish off this problem. And then take out a different color. I do want you to make an XY table here. You may have had a teacher call it a T-chart or something like that in the past. But an XY table, we know that 0 would have a value. We have this equation. Let me rewrite the equation here. It was y equals 0.3 to x plus 57.51. Okay, so that's what the equation is. So if you plug in x into that equation, you get 0 for this part. It goes away. You just have 57.51. On the graph, I want you to plot that point, 0 and 57.51. So here's 0, 57.51, here's 55, so you're approximating it, but it'd be about right there. So different color, that's your y-intercept. If I plugged in, I wouldn't want to plug in 1, that's going to be way too close to really make any significant difference. So I want to get, I would say at least 2, maybe 3 more values. I'm going to go with 40, 80, and 120 for my x values. That will give me a nice solid line. It will let me check and see that I have a straight line. If I plug in 40 into this equation, let's see what that gives me. So I'm going to have 0.32 times 40 plus 57.51. That gives me 70.31 right here. So 70.31, let's plot that point, 40 and 70.31, so just barely above 70 right there. So I got it pretty much right on it, but that's essentially where it's going to be. Can't get much better than that with that. And now let's try 80. So type in 0.32 times 80, and I'm going to add 57.51 to that again. I get 83.11. So 83.11. Go over 80, go up to 83.11. 85 would be right about there, so a little lower than that. There's a new point. Notice if I draw a straight line, these are all going to be right on that line. And finally 120. Let's try that. 120. 0.32 times 120 plus 57.51. That gives me 95.91. And so finally, let's plot that point. 120. This was at 96, so it's basically going to be right on top of that point right there. And if I were to draw a line, a nice straight line, and connect those points, they should all lie on the same line because I use the same slope. Let's do that in a different color. It looks good there. And so what that's saying is the vertical distance from each of these black points to the red line, that's the closest I could get all of them in terms of the total sum of the distance, or the squares of the distance is, I think, a little better way to say that. That's why it's called the least squares line. That is the line of best fit. The best fit for all that data is right there. Okay, one more minor thing to add here, and we'll be good to go. So right here, I just want you to remember where this comes from later when you look at this. This was for part D right there, and so was this. This was for part D. Okay, so that's where that stuff came from. I think that'll do it. Alright, nice job. You made it through, and use this and the other examples in your book. We just went through one altogether. There's a couple more in your book like this. Use those to help you out with this lesson too. Again, not going to assign a cumbersome amount of problems like this, but yes, it's relatively tedious. You are going to have to go through the steps here. If you have a calculator that's fancy and can check this without you actually typing in all these values and finding this sum, if you have one of those statistical calculators or a graphing calculator, you can use that to check your answers, but you are going to be required to show me the whole process. Show me all the steps and show me that you know how that's done. Okay, hopefully that went well for you, and go back and review if need be any parts that you missed or need a little extra refresher on. And have a good morning, afternoon, night, whatever time it is for you, and I will see you guys later.